Welcome back to AI.Code.Cast. Today we're taking a deep dive into a problem that's kind of like a classic in coding interviews. And it's a fantastic way to stretch your algorithmic thinking muscles. The valid anagram problem.
Yeah. This is one of those problems that sounds super simple at first,
Right.
but it can lead to some really clever solutions.
Oh, absolutely. And it really shows how just like a little bit of cleverness can make a huge difference in how efficient your code is.
Totally.
So for our listener who might be like, wait, what's an anagram? Let's break that down.
Yeah.
Imagine you have a word like cinema.
Okay.
An anagram of that word would be any word that you could make by just rearranging those letters.
Oh, like Iceman.
Yes.
Perfect. You got it.
Same letters, different order.
Exactly. So the valid anagram problem is basically asking you, given two strings, figure out if one is an anagram of the other.
Right.
Now, obviously, if we were just playing around with words, we could just try rearranging them in our heads.
Yeah.
But in coding, we need a more systematic approach. You need an algorithm.
We need an algorithm, exactly.
Yeah.
And like a lot of coding challenges, there are tons of different ways to solve this. Some are more intuitive, some are way more efficient.
Absolutely.
So let's put on our coding hats and brainstorm here.
Okay.
What's the first thing that pops into your head when you hear this problem? Like if you were given this in an interview, what would your first thought be?
Well, I mean, the most straightforward approach that comes to mind is generate all possible rearrangements
Okay.
of one string and then just see if any of them match the other one.
The classic brute force.
Exactly.
Just try everything until something sticks.
Yeah. Like try every key on your giant keychain and see which one unlocks the door.
I love that analogy.
Yeah.
And that makes it so clear why brute force, although simple, isn't always the best way to go.
Yeah, especially if you have a really long string.
Exactly.
Yeah.
Especially if you have a 10-letter word. The number of possibilities is just going to explode. So brute force is out.
Yeah.
What else could we consider?
Well, let's think about the core idea of what an anagram is.
Okay.
They use the same characters, but they're arranged differently.
Okay.
What if we could create some kind of a standardized fingerprint for each of the strings based on the characters?
Okay, a fingerprint. I like where you're going with this.
Yeah.
So two strings would have the same fingerprint if and only if they're anagrams of each other.
Exactly.
How do we create this fingerprint, though? What does that even look like?
Well, what if we sorted the characters in each string alphabetically?
Oh, okay.
And if the two strings are anagrams, they'll have the same characters, right?
Right.
And then once you sort them, they'll be in the same order.
Ah, I see.
Yeah.
So if we sort both strings and then they end up being identical, boom, we know they're anagrams.
Yeah, it's like if you have two sets of Scrabble tiles,
Okay.
right? And you arrange them alphabetically.
Yes.
If the two sets are identical, you know they had the same letters to start with.
They just started in a different order. That's such a good analogy.
Yeah, it's a visual way to think about it.
I love that. And the great thing about sorting is most programming languages already have sorting algorithms built in, right?
You got it. Super easy to implement.
So you don't have to reinvent the wheel. You just sort both strings and compare them.
Exactly.
Anagram detected.
Or not.
Or not, exactly.
Yeah.
But let's talk about efficiency for a second.
Okay.
We know that sorting, especially with really large data sets, can sometimes be a little bit slow. How does this sorting approach stack up in terms of what we call in the coding world, time complexity?
Okay, so you're right to think about efficiency.
Yeah.
Most sorting algorithms, the good ones anyway, have what's called a time complexity of n log n, where n is the length of the string. So what that means is as the string gets longer, the time it takes to sort it grows a little faster than just linearly.
Okay.
But it's not super terrible.
Gotcha. So it's not the absolute fastest,
right?
But it's not like the end of the world.
Yeah.
What about space complexity? Do we need to use a bunch of extra memory to do this sorting?
That's a good question. A lot of sorting algorithms can be done what's called in place.
Okay.
Meaning you just rearrange the elements in the string itself.
Gotcha.
You don't need to make another copy.
Oh.
So you can often get away with a space complexity of O of 1.
Oh, wow.
Which is constant. That's excellent.
And that's really good. So sorting gives us a pretty decent solution here. It's easy to understand. It's relatively easy to implement. And the space complexity is fantastic.
Yeah.
The time complexity maybe isn't the best.
Right.
But it's definitely manageable in a lot of situations.
A lot of times it'll be good enough.
Right. Exactly.
Especially if you just want your code to be really clear and readable.
Totally. This is already making me understand this problem so much better.
Good, good.
But I have a feeling you have some more, maybe even more efficient approaches.
Oh, of course I do.
That we could explore.
We're just getting started.
Awesome. Can't wait. Welcome back to AI.Code.Cast. Last time we were really getting into the valid anagram problem.
Yeah, we talked about that brute force approach.
Right.
And then we started getting a little fancier with the sorting.
Yes. Sorting felt pretty good. It was simple.
Mm-hmm.
And the memory usage was pretty low.
Yeah.
But, I always like to see if we can squeeze out even more performance.
Of course, always.
Is there a way to, completely ditch the sorting step
Okay.
and still figure out if two strings are anagrams?
Absolutely.
Okay,
Yeah.
tell me more.
So remember how with sorting, we were trying to create that standardized fingerprint?
Right, based on the characters.
Exactly.
Like alphabetizing our Scrabble tiles.
Exactly. What if instead of sorting, we just counted how many times each letter appears in each string?
Ooh, okay.
If the counts are the same, then we know they're anagrams.
I like that, yeah.
Regardless of the order.
It's like taking inventory of our Scrabble tiles instead of putting them in order.
Exactly.
Okay, but how do we keep track of all those counts in a way that the computer can easily work with?
That's where a hash table comes in.
Okay.
You can think of it kind of like a spreadsheet.
Okay.
Where each row represents a letter.
Uh-huh.
And then the cell in that row stores the count.
Oh, okay. So like for cinema, we'd have like a row for C with a count of 1, a row for I with a count of 1, a row for N with a count of 1.
Exactly.
I'll be seeing it.
And then we do the same thing for the second string, and we just compare all the counts.
Gotcha. And if they match, anagram.
Anagram.
I'm already seeing how this can be faster than sorting.
Mm-hmm.
We're not moving things around. We're just counting up.
Incrementing, yeah.
What about the time complexity with this hash table method?
Ooh, this is where it gets really interesting.
Okay.
In most cases, accessing and updating stuff in a hash table takes constant time. So we'd go through each character of the first string, right? Increment the count in the hash table.
Yeah.
That takes ON time.
Okay.
And being the length of the string.
Okay.
We do the same thing for the second string, another ON.
Gotcha.
And then we compare the counts, also an LN.
So overall, it's still ON, just like sorting.
Same big O.
But it feels like we're doing less work.
You are absolutely right.
Okay.
They have the same big O notation, but in practice, the constant factors involved in hash table operations are usually way smaller than with sorting.
Okay.
So for really big strings, this is going to be noticeably faster.
That makes sense. We're not doing all the comparisons and all the moving around that comes with sorting.
Right.
We're just tallying things up.
Yeah, it's much simpler.
Okay, what about space complexity? Don't hash tables take up more memory than sorting in place?
That's a great question.
I try.
So it kind of depends on the range of characters we're dealing with. Like if it's just lowercase English letters, our hash table only needs 26 slots.
Right, one for each letter.
Exactly. That's fixed, so our space complexity is 01.
Wow, so for limited character sets, that's fantastic. What if we were using Unicode?
Oh, good point.
Where there's thousands of possible characters.
Yeah, that could get big.
Yeah.
In those cases, the size of the hash table could get pretty large.
Right.
So the space complexity might become ON in the worst case.
Okay.
Where all the characters are unique.
So there's a trade-off there.
There's always a trade-off.
More flexibility, but potentially more memory usage.
Yeah, gotta weigh your options.
Okay, I'm seeing that. It's like classic software development trade-offs.
Yep.
Sometimes you sacrifice a little space to gain some speed, or vice versa.
Exactly. Pick your poison.
But overall, this hash table approach seems like a really powerful way to handle this problem.
It is.
And efficiently.
Very efficient.
Which makes me think, you said there are optimizations we could make?
Oh, we're just scratching the surface.
Really?
Yeah.
Can't wait. Welcome back to AI.Code.Cast. We've been having so much fun with this valid anagram problem.
Yeah, we've come a long way.
From brute force to sorting, hash tables.
All sorts of good stuff.
It's been really cool to see how each solution gets more and more refined. And last time, we left off with that hash table approach, which felt like a big jump in terms of efficiency.
It is very efficient.
But you hinted that there's even more we could do.
Oh, yeah.
To optimize it.
Always more optimization.
I'm ready. What other tricks you got?
So let's think about that hash table method for a second.
Okay.
We create the table. We populate it with the counts. Then we compare the counts.
Yeah.
What if we could do all that at the same time?
Simultaneously. How would we even do that?
Okay, imagine we have a single loop that's going through both strings at the same time.
Okay.
As we hit a character in the first string, we increment the count in our hash table. But here's the key. When we get to a character in the second string, we decrement the count in that same table.
Ooh, I see what you're doing. It's like we're balancing a checkbook.
Exactly.
Deposits for the first string.
Yes.
Withdrawals for the second.
And if everything zeroes out at the end, we know they were the same.
That's such a good way to put it. And with this, we could even spot problems early on, right?
Right. Like if you try to decrement a count and it goes below 0, you know they can't be anagrams.
You don't even have to finish looking at the strings.
You don't need to keep going. You're done.
That's so smart. But, okay, this single loop thing, how do we make sure we're like putting each character in the right spot in the hash table?
Okay, so this is a cool trick.
Okay.
Especially for lowercase English letters.
Okay.
Each character has what's called an ASCII value.
Right, right.
It's just a number that represents that character. So if you subtract the ASCII value of A from the character's ASCII value, you get a number between 0 and 25.
Right.
Which we can use as the index in our hash table.
So A goes in slot 0, B in slot 1, and so on.
Exactly.
Like assigned parking spots.
Yeah, and it's super fast because you don't need any fancy calculations.
Right, you just calculate the index directly from the character.
Boom, right there.
This is feeling so optimized, like we're going through the strings once, counting up and down as we go, putting things in the right spots.
It's very efficient.
But I'm always curious about time and space complexity.
Of course, always important.
So, with this super optimized version, what's the deal?
Time complexity is still ON, because we're still going through each string once.
Right.
But it's often way faster in practice.
Gotcha.
Because we're doing less work overall.
Like taking the express lane.
Exactly. No traffic lights.
Love it. And space complexity.
So if we're using lowercase English letters and that fancy indexing trick, we still have a fixed size array, 26 slots.
So still O1.
O1. Fantastic.
Wow. So we've optimized both time and space. Is there anything we should watch out for with this approach? Like any limitations?
Yeah, the main thing is that fixed size array. Works great for lowercase English letters.
Right.
But if we had like Unicode characters, you probably need a hash map instead. Which might use a bit more memory.
So again, trade-offs.
Always trade-offs.
Speed versus flexibility.
Choose the right tool for the job.
I love that. This has been such a cool exploration of the valid anagram problem.
A fun one.
We've seen 3 really different approaches. Sorting, frequency counting, and this supercharged single loop version.
Yeah, and they all have their pros and cons.
Right. Sorting was easy to understand and implement.
Yep.
Frequency counting was more efficient. And then the single loop just took it to another level.
For certain situations, it's the best.
I bet our listeners are feeling way more confident about this problem now.
I hope so.
And hopefully, this has sparked their interest in algorithms in general.
There's so much to learn.
It's amazing how a problem that sounds so simple can lead to so many cool techniques and ideas.
It's like a puzzle.
Absolutely. That's the beauty of coding. Always something new to discover.
Always learning.
Thanks for joining us on this episode of AI.Code.Cast. We'll be back soon with more deep dives into the world of algorithms.
See you next time.
Happy coding.